Good morning, everyone. It is week 2, day 2, and we are mostly going to talk about functions today. We went over the basics of ARM32 on Tuesday, and we're going to knock off a big rest of the chunk today. So let's just get going on it. If you check your ASM demos folder, it's got demo code for basically everything you'd want to do in ARM32. So let's look at functions. Okay. The big thing about a function is this right here. The alias vim and vim again. Some context out of that. All right. So anytime you do a function, there's some boilerplate you should do. So this here is a function that'll just add two numbers together. We talked last time about how you make a function name, and that name could be called from other .o files and things like that. You do it with .global. That adds the add function to the symbol table, marks it as a function you can call, basically. And then we have this push thing and this pop thing here. Now technically for this function, we don't need it, because let me explain what it does. So there's something called the stack. You guys might remember that from your other computer science classes. Every time you do a function call, remember the stack pointer goes down, and then when you return, the stack pointer goes up. Yeah, so when you push onto the stack, this moves the stack pointer down. Technically, push and pop are not ARM32 commands. They're pseudo commands. These things generate assembly commands for you, just to make life easy. And so what this does is that this pushes register 14 onto the stack, and then the stack pointer moves down. And then we push the registers 4 through 11 onto the stack, and the stack pointer moves down. And then when we return, we restore the values of registers 4 through 11, and we do that first because it's a stack, right? Last in, first out. So this saves the registers that are supposed to be saved. Remember how I said registers 4 through 11 are kind of the registers you have to play with. That's why they're safe to play with. It's not automatic. When you do a function call, they don't automatically get saved. It's your responsibility to save the previous function's registers 4 through 11. 0 through 3, registers 0 through 3 don't get saved between function calls. So the first thing we do is we save the registers from the previous guy, and then when we're done, we restore them back in. And when we do a function call, we rely on that function to save the registers and restore them as well. And then finally, we do a pop program counter, and what that's going to do, it's going to restore the value from the link register, not into the link register, but into the program counter. The program counter is register 15, the register you're not supposed to mess with. And the reason why this works is because register 14 is the return address. That's the address we came from when we did a function call. And so by restoring the link register into the program counter, the next line of code to run is that line that we came from, technically one past the line that we came from. And my advice to you is just to learn to just write this as this 4 lines here at the beginning, these 2 lines at the bottom. Just write them as boilerplate. If you ever need to optimize it, you can actually look at which registers you're messing with. In this case, we're not actually messing with any of the registers 4 through 11. So in this case, it would be correct to comment the push 4 through 11 out, because we're not, we're not changing them. But if we ever had a function call, then it would absolutely be critical that we save those registers, right? or yeah. Or you can just get into the habit of doing it, but it's more of an optimization to not preserve them. Okay, and then the actual function body is here. So add R0, R1, and return the result into R0. Now, you can have 4 function parameters passed to a function before things get complicated. And so for this class, I don't think we're ever going to pass more than 4 parameters to a function. The first parameter passed in, the first one in the list here, when you have a function prototype, the first function is passed as register 0. The next one is passed as register 1. If we had a third parameter, it'd be passed in register 2. If you had a fourth parameter, it'd be passed in R3. And the return value always goes into R0. So that's why R0 through 3 are not saved through function calls, is because they're used as the interface for the first 4 get passed in that way, and then R0 is the return value. So if you had something in R0 before, you did a function call, it's gone now. Okay. And yeah, so that's how you make a function. Now we need to learn how to call a function. Okay, so so we got here BL. Okay, so BL is branch with link, and branch with link is how you do a function call. Simple as that. So if we got a C function call, got several C function calls. We got one called prompt, one called readint, one called print signed compare. Main is here in assembly, but I'm doing my I/O in C. Okay, and this is kind of how I expect you to do your input and output for most of this class. Okay, when you're doing a C in or a C out, whatever. Until we get to the point where you learn how to do this in assembly, which I've said before is not easy. Reading and writing strings isn't too bad, but if you want to read or write a float, like my lord, I'm not cruel enough to make you write that. Usually, most assembly classes have you write your own, thing to convert a string into an integer. Integers aren't too bad. Floats are just annoying as well. Okay. So that's it. So that just calls the function. Simple as that. Prompt doesn't take any parameters. Let's see if I have. Yeah. Only. So prompt takes no parameters and returns no values. That's why you don't see anything coming in and out of R0, because it doesn't care. Okay. So prompt is just going to print to the screen. Please enter 3 integers. Da, 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 da. So print function, printf, is found in C standard IO, which is what it's called in C++. In C, it's called standard IO.h. And it is a complicated function, and probably should have a lecture at some point on printf just on itself. And scanf is the counterpoint to printf. You might notice the ampersand there. The ampersand everybody forgets. Scanf is the equivalent of cin. So this is going to read an integer. The format string there, %i, means read an integer, and it's going to read into x. It reads. You technically point at an integer, and it reads from the keyboard, and it writes it into that spot in memory. So don't forget the ampersand. If you forget the ampersand, you will segfault, because you're going to be writing to memory address 0, which is the null pointer, which is segfault time. The rule is you can do IO in C and C++ and use a generated assembly. Nah, not using the generated assembly at all. Nah, don't do that. No, just use it in C and C++. It's way too complicated. I don't want to see you guys using generated assembly at all in this class. It's ugly. It doesn't teach you anything. The reason why I told you that G++ dash capital S is useful is if you ever forget like how to do a function call, then you write a C++ program to do a function call, you compile it, and you look at the assembly to see what it translates to. In fact, there's a website that I've been meaning to introduce to you, and this seems like a good time to introduce it. And it is called Godbolt. Okay? Or Compiler Explorer. Named after a guy named Godbolt, which is a pretty cool last name. I mean, I'm gonna grant him that. So, so Godbolt translates your C++ code into assembly, and if you mouse over the lines of code, it'll show you the corresponding line in assembly. So let's I don't know, int x equals 7, int y equals x plus 3, and let's turn off the optimizer. And there you go. So this is pushing something onto the stack, subtracting the stack pointer down by 12. That's going to make room for 3 integers. It's moving the stack pointer down, right? Because stack allocated variables come off the stack. So that moves the stack down by 12 bytes. An integer is 4 bytes on our system, right? We add stack pointer plus 0 and save that into register 7. That's probably why it's saving register 7. I don't know what it's doing with the register 7 in particular, but it is. It then moves 7 into register 3. Yeah, so that line right there. You see how I hover over it? It highlights the assembly that line of C++ translates into. So, and this doesn't have all that stupid boilerplate stuff that you could more or less ignore, right? It actually gets to the heart of the matter, and you can mouse over things and see how it do. Okay, and so if we had a function in here called int Bob return 42, put it on its own line so that, yeah. So if I mouse over this here, you can see it's moving 42 into R3, then R3 gets moved into R0. R0 is the return value, right? And then it restores the stack and returns, right? That's cool. Load register, immediate calculated. That's neat. It's got explanations of the different assembly commands. That's very cool. Never seen them before. I wonder if that's new. Maybe I just never saw it before. I don't know. Okay, so yep. So if we set y equal to Bob plus x, let's say, you see the thing dynamically recompiles in real time. It's really cool. So you can see here we've got a function call to Bob. Okay. And then it's moving the return value. The return value of Bob is written into R0. It's going to return 42. And 42 gets put into R2. It then adds R2 and R3. R3 is X, right? It just stored X, and then it's loading it again because it's highly unoptimized code. When you have unoptimized, when you don't have the optimizer turned on, you do a lot of, really bad things in terms of efficiency, right? It's correct, it's just very slow. So it stores to RAM, then it turns around and reads from RAM. So calls Bob, writes the return value into R2, adds R2 and X together, and stores the result. And then it's going to return 0. So 0 goes into R3, R3 goes into R0. It adds 8 to R7. I don't know what R7 is. That's basically when we're done. Oh, okay, it moves. That's so stupid. So it then puts that into the stack pointer, so it puts the stack pointer back up. It basically deallocates all the local variables, x and y, get deallocated. It makes room for two ints, right, x and y, and then when we're done, it moves the stack pointer back up. Right, it could just add 8 to the stack pointer, but it's unoptimized code, so yeah. And then it restores. So it saved register 7 and LR. Then it restores register 7, and you see how LR gets restored into the program counter, and then that goes back to whoever called main, which is underscore start. Okay. You just write anything in C++ and it translates it. Yeah, just make sure that you're doing ARM. By default, Compiler Explorer does x86. So if you see something like what is the default? Something like that. Come on, it's not a big program. Okay. It really is simulating Microsoft Visual C. Bad gateway. Wow. Okay. Well, if you see garbage looking stuff, you're probably set to x86. So come up to ARM 32-bit GCC and just pick ARM GCC trunk. That's the main version there, and it will generate the ARM assembly for you. So it translates from C++ to ARM, but not in a fast way. Well, if you want, no, it's perfectly. This is the output of a compiler. Compilers by default give you bad, unoptimized code. It's when you turn the optimizer on that you see that you get you get the optimized code. So in this one, it just puts 42 into the return value and then returns, and then for main, it returns 0. Easy. Okay. There's no call to Bob at all. Why? Because x and y are not used for anything. So why bother doing that computation at all? It just deletes it. It never even calls the function. If we were to cout y, then then you'll see that it does a branch with link, so it's going to call, that's cout there. Interesting. Lower 16 bits, upper 16 bits. Interesting. Why would it? Okay. Move word. Okay. So then it calls the double left arrow operator. So that prints whatever's in R0. It then loads the return address from R0 into R3. Moves that, subtracts 12 from there, loads from that into R3, adds R3. And then Bob is still optimized down to just returning 42. So remember when you do a cout y, it returns the value of cout. And so what it's doing, it's taking the return value of it, doing some stuff, then it's going to call the inline somewhere over here. Okay, yeah, there it is. It's going to do a flush. So it's going to put a char, which is going to be the new line character, then it flushes the output buffer. And then it returns 0. So, yeah. So Compiler Explorer, Godbolt, super cool stuff. All right. So coming back to my code, we got a function here in C called prompt and a function here in C called read_int. Neither of them take a parameter, but readint does return a integer. So this will read a integer from the keyboard into x and then return the value. And so here in the functions thing, when you call readint, R0 afterwards will now have whatever number they typed in. If they typed in 42, it returned. R0 has the value of 42. So I'm moving that into register 4. And I also move it into register 7 so that I have 2 copies of it for some reason. And then I call read integer again, and I save the results of that into R5 and R8. There's probably some reason why I'm doing that. And then I call readint again and save the results of that into R6. So, I'm then going to compare, what am I supposed to be doing here? I forget. Why do I not have the C++? Well, what it's going to do, it's you type in 3 integers, it tells you. It then compares the first 2 using signed comparison and unsigned comparison. If you wondered where types came in, like how do you know if a number is signed or unsigned? You don't usually in assembly. You kind of have to know, like you know if you know. But like you can tell the comparison operation whether or not you're doing a signed comparison or an unsigned comparison. And then, okay, so it compares the first 2 to see if they're greater than, equal, or less than, treating it as a signed integer, then again treating it as an unsigned integer, and then it does a, it tells you if the first number entered is between the second number and the third number. So if you type in 3, 0, 5, 3 is between 0 and 5, so it'll tell you that. Okay. And then we have more functions. No parameter void takes 2 parameters. And so you can see how printf works here. So printf has something called a format string, which are strings that have these magical characters in them that have the shift 5, the percentage sign on it. Why do you push and pop to stack when you do a function call? Because you need to save the registers. Registers 4 through 11 are supposed to be preserved between function calls, and so you preserve them. You save the previous guy's register values to the stack, and then when you're done, you put them back. It's like those registers are not supposed to change when you do a function call. So you save any of the ones you're going to change. It's overkill to save too many of them, but it's fine. It's correct. Slow but correct, and you can optimize it later. So you got 2 %i's here. The first %i will have the value of x put in. The second %i will have the value of y put in. And so it's probably good for you guys to see printf in the wild finally. It's still used today. A lot of people like it more than cout because it's more compact. You can, especially if you're outputting a lot of, if you're gonna output a lot of variables, you can do like 3, 4, 5, x, y, z, w, a. That's way more compact than cout x, followed by space, followed by y, followed by a space, followed by a z, followed by a space, followed by w, followed by a space, followed by a, followed by inline. You can see that the cout version is almost twice as long, right? It's called chevron hell. You just have all these chevrons everywhere. And so there's something called the FMT library, which is now part of the C++20 standard. And it does something like printf, but more safe. Printf is an enormously unsafe function. Like if you it doesn't know if the integer here that you say you're going to print Like it doesn't know if x is actually an integer. There's no type checking, right? Compilers nowadays will warn you, but like if you pass in a float here, it'll treat the bits of the float as if it was an integer, and who knows what will happen. Okay. So yeah, it might hurt your inline scrente, but printf's pretty. I'm not sure I didn't save anything. It's pretty common, and if you ever go to work in SeaWorld, you gotta know printf and scanf. They're core functions that everyone knows, and they also just kind of pop up in different places. Like I was playing a video game that was scriptable, and the way you printed things in it was using essentially printf. You'd have a format string and the percentage D and F and things like that, and you'd pass, like it was using printf, and it's just in this video game, So. Used a lot, especially in everything C++. Not in everything C++, and everything C. Everything C, and then it just shows up in a lot of places. C++ people, some people actually do use printf and scanf in C++. But CN and CI is probably more common. Yeah. It's fast. It can be. Format library is actually, I think, faster. So the future is fmtlib. This is the open source library that got included into the standard, kind of. The version included is slightly different from it's slightly different from the one on GitHub. It's a safe alternative to standard I/O and I/O streams. So they should have a running time. There you go. So FMT is faster than printf. Cout is not fast, by the way. And Boost's format is very slow. So, yeah, but printf's pretty fast. That's one of the reasons why people use it. Compile time, pretty bad. And Boost takes the cake with compile times. I don't know why. They're every time you include Boost, like there's a noticeable lag in your compile time. Okay, so that's the future. You can learn format on your own, I guess. Okay, so we got all these things, and you see here how we're passing in a parameter as int here, and we're passing in an unsigned int here. You will see no difference in the assembly code. You just put R0 in, and there's no types, but the C++ code will treat it as signed here and unsigned here. Okay. Python's format is one of your favorite things, yeah. Okay, so let's and so this one's passing 3 parameters in within. Let's take a look at within. So you'll see that within is, well, we've kind of hidden it in our macro here. But I wrote a macro, and so rather than repeating this code over and over again, compare R4 and R5, move R7 into R0, move R8 into R1, move R6 into R2. The reason why I keep doing this every time over and over again is because the parameters are always going to be the same, right? X, Y, and Z, X, Y, and Z, X, Y, and Z. That's why I save them into R7, R8, and R6. And then somewhere within here, yeah, we're going to actually mess with R4 and R5. That's why I made 2 copies of them. I saved X into both R4 and R7, and I saved Y both into R5 and R8, and the reason for that is because I am messing with them. I'm subtracting the numbers to do a betweens comparison. Okay, so what is this my if thing here? This is a macro. It's doing these 4 lines of code. And if you ever find yourself in assembly writing the same 4 lines of code or whatever over and over again, then you can make a macro like this. This is not a function. It is a macro, and basically it just the assembler expands it out to the. It's like a copy paste kind of thing, right? So you have 4 lines of code, and you just want them to appear over and over again. So you just type my underscore if, and it will expand my underscore if to these 4 lines over and over again, and it makes your code a little bit more readable, arguably. Macros can take parameters and other things like that, but I usually don't mess with that. I just use it for block copying and pasting code if I have to do it over and over again. So, so we compare x and y, and we branch with link if less than. Remember that last time? You can add a suffix to basically anything. And so we're going to do a function call. We're going to call the less than function if we're going to do the less than function if and only if x is less than y. We then do the comparison again, and you're like, wait, why do we have to do the comparison again? If it does not call less than, then what? Then it'll just move on, right? And then we can check this one and we can check this one. Well, what if it was less than? If it was less than, then that comparison register is going to get exploded. Remember, there is one secret register for doing comparisons, and if you ever do another comparison, it resets the secret comparison results register, the CPSR. So you have to redo the comparison every time. There's probably a different way you could structure it. Like if I did a branch, you wouldn't have to do that, but yeah. So we compare x and y. If x is less than y, we call the less than function, which prints the screen x is less than y. We then redo the comparison, and if the two are equal, branch with link if equal. If x is equal to y, then it calls equal to. Do the comparison again. If x is greater than y, it calls greater than. And then we come down here. Now we're going to do unsigned comparisons. Okay? And so unsigned comparisons are a little weird looking. Branch with link if carry clear. And now branch with link if carry set. And you're like, carry, I thought you said last time that had to do with like if you add 2 integers together and a bit carries out the last bit or something. Yeah, that's what it's usually used for, but it's also used for when you do a comparison. It's also used for telling you if the thing is less than or greater than if those bits happen to be unsigned. Because remember, assembly doesn't know if those bits are signed or unsigned. It doesn't know. And so it does both less than, greater than, equal to, using signed and unsigned. It does all of them, all at once. And so if you want to know if it is less than in the unsigned world, then you check to see if the carry bit is clear, which again makes no sense, but whatever, that's how it is. And if you want to know if if x is greater than y, if x was an unsigned integer, then you check to see if the carry bit is set, and then you call unsigned greater than. And then finally, let's see if x is between y and z. So what is this? What is the logic here? I'll throw this open to you guys. How is this figuring out? I'll give you some labels here. R4 is x, R5 is y, R6 is z, or z, as some people call it. How is this telling us if x is between y and z? What's the logic here? What's happening here? Anyone? Let's see if we can figure that out. It is doing x is equal to x minus y, but how is that telling us if x is between y and z? It's subtracting x from y. So if x is positive, it has to be greater than y. That is correct. And then what about for this one? It's seeing if the value is between. Yeah, well, how is it seeing? Yeah, I told you, like, we're seeing if it's between, but how? How is doing two subtractions telling us if x is between y and z? If subtract R4 is positive or 0, then x is greater than or equal to y. That is correct. The final product of z minus y. So this is z. So z minus y. R5. If it's greater than x, then x is between y and z. No, that's not true. What if we have 10, 15, and 20? Right? X is 15, y is 10, z is 20. Z minus y is 10. 15 is greater than 10. So what is this doing? What's the logic here? But thank you for answering. I want to say that it's far better for you to participate and answer and get it wrong than it is to sit there like a bump on the log, like half the students are doing right now. Take a shot, take a crack at it. You won't get a hit if you never take a swing at the bat. Saving the product of y minus z and then saving it to R5, that is what we're doing, but why? This is in fact computing, z minus y and saving it into y. And why are we saving it into y? Seems odd. Remember, the macro always compares R4 and R5. If sub R4 is positive or 0, okay, then x is greater than or equal to y. In turn, sub y being positive means x is less than or equal to z. There's no x here. This is z and y. So if z minus y is positive, that doesn't mean that x is between it, right? It's trying to check if y is greater than z. It is subtracting z minus y, but it's comparing R4 and R5. So it's comparing the result of of this, right? So this is saying x is equal to x minus y. Leave this here. And then we're saying y is equal to z minus y. And then it's going to compare x, y. Right? And then it's doing BLCC. BLCC is unsigned less than. So it's treating the result as an unsigned integer, not a signed integer. So if it's a negative number, it'll underflow and wrap around to a very large number. And then again, we're doing a unsigned comparison here. Yeah, here's what myif is doing. This is myif. These 4 lines up here. It's comparing R4 and R5, and then it just moves the registers into R0, R1, and R2 so that the functions can print them. So we constantly use our saved values of x, y, and z and put them into parameter 1, parameter 2, parameter 3 so that we don't have to constantly do that over and over again. So what is this doing? It is not swapping. No, you guys. It's not setting x to 0 either. You understand the first subtraction, but the second one's confusing you? Sure. Yeah. So if x is smaller than y, if we're treating this as an unsigned integer, it'll underflow and become like 3, 4 billion, whatever, right? And so BLCC is saying if you have an unsigned integer, if the first number is less than the second number in the unsigned, treat it as an unsigned number. So it's saying is x, like less than y, right? It's kind of like casting it to an unsigned integer. So y is holding the difference between z and y. So if we have x is 15, y is 10, z is 20, we have 10, 15, 20, right? So z is 20 minus y is 10 gives you 10. So y now holds the range, the spectra between y and z. How wide is the range? Okay? And z, or x, now holds how far to the right of y x is. So it gets normalized. Basically, it's normalizing x and z. It's setting y, because y is the starting point, right? So it's basically making y to be 0. So if we had 2, 4, and 6, y is 2, x is 4, z is 6, then x is now 2 and z is now 4. And the reason why we do this is because if x is to the left of y, if it's an unsigned integer, it'll underflow and become 4 billion. When you do an unsigned comparison like this, 4 billion is bigger than 4. Okay? And so what we're doing is we're seeing if x is less than y. Y now holds the range. So if you have a range of 10, so that means z was 10 to the right of y, and x was 5 to the right of y. If 5 is less than 10, that means that it is between y and z. This is like some big brain thinking, but it's actually a very fast way of doing a range comparison, a between computation. So if x was to the left of y, it underflows and becomes maximal. If it's to the right of z, then let's say x was 30 to the right of y and z was 10 to the right of y, then x is not between y and z, right? Then x would also be bigger than z. This is the reason, by the way, why unsigned integers exist, is that it actually allows you to do some very interesting optimizations with if statements, because you only have to do half as many comparisons. If all you had were signed integers like in Java, then you have to compare x being greater than y, and you have to compare x being less than z. With this, you subtract x from y, and it will underflow, and then you only have to do a single comparison between x and z. And remember, comparisons are expensive. You can think of them as an 8-cycle cost, even though it's a bit of a simplification. And so by doing it this way, you only need one comparison really instead of 2. And so yeah, that's what's going on here. This is like some big brain assembly. Okay. So this is an unsigned comparison, and then it does it again, because again, if we do this function call, it will clear the comparison register, and we can't do that one. So how do we build this? So we've got all this assembly code here, G++, 7, and we're going to combine this with readent, not G++, GCC, sorry, readent.c. And that is how you merge together two things. This is going to link together your assembly code and the C code. There's better ways of doing this if you have makefiles and things like that. But if you're just doing a simple thing like what we're doing, that will make all of the functions in readent available to the assembly in number 7. If you just compiled this by itself, it'll assemble just fine. It doesn't compile, it assembles just fine. But when you try building the executable, all those functions that you thought you said, I'm calling readint, I'm calling this, I'm calling that, it can't find them in the link step. So the link step is when it takes the .o files and puts them together. You might notice the .o file here is CCN K5 K8. That's because, like I told you, it generates a .o file. Every time you compile something, it generates a .o file and deletes it later. So if we tried, like, statting this, tell me about this thing, it doesn't exist. It's been deleted already. Okay. So, yeah, all those temp files get deleted if you don't tell it to save it. So in order to compile this properly, you have to just pass in both your assembly and the helper.c file. This is how you make it work. Okay? And if you wanted to do this readint thing in C++ instead, readint.c to readint.cc. Then what you have to do is this externc. And if you do this, this turns off name mangling C++. Okay, this is the crucialest thing you need to know if you want to make C++ interoperate with assembly. You're going to have to get used to using externc. And there's an open curly brace here, and that curly brace goes shift 5, matching curly brace all the way down. Okay, so I'm wrapping this entire document in extern double quote C close double quote. And what this does, it turns off name mangling. By default, C++ changes the names of functions to include the parameters and such that they take. That's what allows overloading to work. You cannot have two functions with the same name. In C++, we do allow two functions with the same name if they have different parameters, and that's how it works. It actually bakes the parameters into the name of the function and kind of hides the fact that the name of your function is now something horrendous, right? So the other uses for externc include integrating with other languages. So C and assembly use the default way of naming functions and calling functions and things like that. C++ has a non-standard way. And so if you ever say externc like this, it will use the standard way of naming functions instead, but you lose the ability to have function overloading. Nothing inside of this block can have, I can't do this anymore, right? I can't have a different readint, even if the function, this would be normally legal C++, right? In C++, you can have one readint that takes no parameters, one readint that takes one parameter, not inside of externc, because now you've got two functions with the same name. Not allowed. Okay. If you do this, you will get a conflicting declaration, because this is inside of an externc block. So that's why we don't just like do it by default. Right? We put it outside. It's fine. Okay. And if you look at the assembly for readint.cc, you'll see that there is one readint that takes an integer. You see that? It's readint I, right? So it bakes the parameter that it takes. Remember, it was readint with an integer parameter. So it bakes the fact that it has an integer into the name of the function. How name mangling works, I don't know. I don't care. It's invisible to me, so I've never really bothered looking it up. But you can see here, you know, underscore Z8. I think that's part of the. Titanium standard, something like that. And then you can see down here we've got the externc version. You see how that is not name mangled? We have externc readint. So that one, the function is just readint. There it is, global readint, no name mangling. Whereas this one is underscore Z8 read underscore int I. Yeah. So this is name mangled, and this one is not. Okay. And all these other functions here that we turned off name mangling on, they're not name mangled either. So, yeah, I've used this in my professional practice to read S. Run the program. 10, 15, 20. 10 is less than 15. 10 is less than 15. 10 is not between 15 and 20. 15, 10, 20. 15 is greater than 10. 15 is greater than 10. 15 is between 10 and 20. So if you want C++ and Fortran to interoperate, same thing. It's externc. It's not extern Fortran. It's always externc. Externc means disable name mangling. Okay. So that is. I think I told you before that C and assembly go together like peanut butter and jelly, or chocolate and peanut butter, or peanut butter and bananas, or peanut butter with anything. The only downside to C++ is that you just need to do this. That's this line right here. That's it. You just do that, and then you can write all your stuff in C++ instead of C. So one extra line of code up top and a close bracket down below, and you're good to go. This is all C++ now instead of C. It looks like C, and it is C technically. All this stuff here is valid C code. Pretty much everything in C is valid C++. Very, very few differences. There's very few legal C programs that are illegal C++ programs, and they mostly involve variable length arrays and void pointers. C is a little bit more permissive with what you can do with a void pointer. C++ says if you point into the void, then the void points into you and doesn't allow as much stuff with it. All right, so ask them first, is the parse score the lowest possible? I think the parse score, so let's take a look at that. CD up, CD into asm first, vim main. So main, I don't think you're going to touch main at all, right? Like it just, you see how I have externc here? Because I'm calling assembly code. This is the other way around, right? Before we had assembly calling C++. Now this is C++ code calling assembly, and once again, we see externc because we're disabling name mangling. We could technically mangle the name and create a function in assembly with the name, the mangled name. That'd be fine. I don't recommend it. Because what if you move to a different platform that doesn't use the same name mangling standards? Itanium's fairly common, pretty standard, but I just wouldn't. I would just do it. I would do it this way. Okay. So the code is going to read X, Y, Z, and W, and then you pick a choice, and it calls a function and outputs it. So that's the driver here. And then you got to write the code. So vim s. So par, I think, is how many strokes I did it in, maybe something like that. So that should be kind of like what you're aiming for. I don't know if it's the absolute minimum, but I think the first crack that I took at it with some minor optimizations. Yeah, foobar at 6. Okay, well, sounds good to me. All right. Yeah, you can probably get it down to about 4, I think. So the boilerplate doesn't count against you, I don't think. Okay. I shouldn't say that. Let me see how I did it. Let's see if up cd asm first. Oh, never mind. I did foobar in 3, not counting the boilerplate. Let me double check that. The label and return aren't counted. Yeah, okay. Yeah, so three strokes. For both of them, total. Yeah. Remember that multiplying is 4 strokes. That is absolutely true. Okay. The book has a lot of nifty things in it that helps in the assignment. Absolutely true. This might be the first class where you actually buy an optional textbook. I talk to my fellow professors. I'm like, have you ever had it? Like, if you have in your syllabus, like, optional, you're taking an English class, optional, buy the shrunken white, Strunken White's Elements of Style. You just toss it on your syllabus. It's an optional textbook. Have you ever had somebody buy the optional textbook? And they're usually like, yeah, this one really dedicated student once who bought it. Like, nobody buys the optional textbooks. This is technically an optional textbook, but it really is, it's really required. It's not required. But I buy it. It's $20. And as McCowan found, it's on Kindle Unlimited. So if you have Kindle Unlimited, you can read it for free. Like I said, I sat down and knocked out the whole book in one marathon pancake session over at Batter Up. And I'm like, okay, I understand ARM assembly now. I think I had my laptop with me and I ran a few commands, but mostly I could just read it and be like, okay, yeah, I understand that. Okay, that's how comparisons work. Okay. That's how and, or, and not work. Okay, got it. So this is a class where you might buy an optional textbook for the first time. I still paid because he's doing the Lord's work. I know, right? Like, never met the guy. He just seems like a cool guy, and the way that he writes his books is just like, fantastic. So, so because this function is being called by C++ main, we need to worry about preserving the registers with push and pop. Remember, the push and pop don't count against your. They're part of the boilerplate. If all you do is modify R0 through R3, then no. You don't need to do a push and a pop. BXLR is good enough. So, if you're going to mess with register 5 or whatever, then yeah, you need to save register 5 and then restore it later. Oh. I'm actually reading it's an actual good book. My lord, it's rare. Yeah. Yeah, I will fully admit to being a fanboy. So, yeah, short, cheap, well written, very useful. Teaches you ARM assembly, really easy. The Bibble. Yeah. Okay, The pictures that popped up on that search. What search? Oh, shrunken white. Should I shrunken white? Dare I? Doesn't look that bad. That's kind of funny. For the sin of forming the singular possessive of nouns ending in s with a single apostrophe instead of the apostrophe s, I say your name is not in the book of life. Depart from me, ye cursed, into the everlasting fire, prepared for the grammar devil and his angels. Okay, it's pretty funny. Not strunk, oh, shrunk. Dare I? I don't know. Oh, okay. Interesting. Okay. Yeah. No, nothing too horrible. Nothing too horrible. Okay. You're college students, you can deal with it. People wearing white crop tops or whatever. Could have been worse. That's always like one of my fears is like, you search for like something live, it's being recorded and Linux, you can have what are called child processes, and so you can Google how do I kill a child, with a fork. It's an actual question that you would ask in Linux. How do I kill a child? Autocomplete turns off. That is too funny. In Linux. It's an actual thing. It's an actual thing, but that's a risky search right there. Get added to the FBI watch list. Okay. Okay. Yeah. So good. I still have my job. All right. What other questions do you have about the ASM first assignment? Because now you know everything you need to know about it. Basically, what you needed to know was saving the registers and restoring the registers to write the functions. Everything else you know already. Anything else? You want any tips? You want to know my my stroke count for any of the other ones? Like I said, the par was when I implemented it and did sort of like a slightly optimal, like no like extra calls to like debugging functions, and like just like took a crack at it, made sure it was correct, cleaned it up a little bit. That's par. Okay. Count on Baz. 11. Probably optimize that. Maybe not. Maybe that's about as good as it can go. Yep. All right. I found a way to use them more effectively. Macros do not change your stroke count, because remember, it still generates the same assembly under the hood, right? Like a macro is an assembler directive. So even if you have 10 things in your macro, a macro call just still counts as 10 strokes because it's still generating the assembly. It doesn't speed up anything. It's just purely a cosmetic thing. Anyone else? For ASM first, I was wondering if you go over how they connect. What do you mean by how they connect? The they connect here, right? Like the C++ code says these functions exist, and they're not using name mangling. And so when you compile it, if you just tried compiling main by itself, you'd get a linker error, right? Because you've promised these functions exist, you're calling them, and it can't find them. If you do this by itself, you're going to get undefined reference errors because these functions are being called. Don't know where they are. So that's why you should use the makefile, because the makefile will do the thing. And this is a link step here. So again, this is kind of one of the things that you're learning these weeks is like about the linker and like how it's kind of important because in real life you're going to end up dealing with makefiles and CMake and things like that, and you're going to be getting linker errors because linker errors are the double zone error, and you have to kind of understand what's happening under the hood. So these are all the functions that are either in main.cc, nm prints the symbol table basically for something. A symbol table is a list of all the functions that are in it and a list of all the functions it calls. And there's also what's called readelf, and you have to pass it dash S for the symbol table. Dash A is a little bit too much information. And so this is a symbol table for main. And so not as useful actually. Okay. It's calling cout, and you can see it's undefined. Okay. It's calling foo, and it's undefined. It's calling bar, and it's undefined. And so what happens when you build the executable, these things that are in the standard library get found. But these things don't get found unless you, in the link step, you give it a list of all the object files together. So if I were to nm foobar.o, you can see there are two entries in the symbol table in foobar.o, and there's a function called bar and there's a function called foo. All right. There's a function called foo, a function called bar, and that's the symbol table right there. Okay. And so when you link together main.o and foobar.o, main.o is calling bar and foo. It's calling it here. And it's like, I don't know where they are. And so the linker, what the linker does is like a jigsaw puzzle. So main is calling foo. It's like, all right, do I see foo anywhere? Oh, it's over here. And then it like takes the code for foo, your assembly code, your compiled assembly code, and it plugs it in. Okay, do I see bar anywhere? Oh, there it is. And that's what these symbol tables are for. It's sort of like a table of contents of like what's in each .o file. And so foobar.o has two things in it. It's got a function called foo, a function called bar. And it tells you which memory address these things are at, if you care. And if we read elf.s foobar.o, you can see memory address 0, memory address 4. It's a global label. Yeah, okay. So read elf. Tell me everything about it. ARM32. ELF is the executable loading format. Unix nerds tend to also be D&D nerds, and so there are things called ELF and dwarf, something like that. It is a Unix thing. It's compiled for ARM. I don't know what else in here actually is going to matter to you guys. Yeah, but the main thing is that the symbol table has got foo and bar in it. And so when you do a compile step, like the one we saw, right here, what that's doing, G++ is invoking the linker. And so main.o's got some needs. It needs foo, it needs bar, it needs baz, and it needs cuz. And it's got these holes in its heart that need to be filled. And so when you do the link step, what it's doing is it's looking for every undefined reference and trying to see, okay, can I find this? Out of all these .o files I have, is that thing found anywhere? And all the linker does is just goes through the symbol table, which is just like a table of contents, list of function names. And if function A calls function B, and function A is in this file, and function B is in this file, it goes click, and it puts it together. Does that make sense to you guys? What the linker does? And if and this is not just for main, it's for any of them. So like if foobar is calling Baz, then foobar would have a note in its symbol table that it is calling a function called Baz that's undefined. I don't know where it is. And so in the linker step, when you put them all together, it's like, okay, let's go through all of our undefined references. Okay, foo is calling Baz. Okay, do we know Baz anywhere? Let's go through the table of contents. Ah, there it is. And so it goes, doop, and it clicks it in. Okay. It's not 3 strokes, sorry, I miscounted. 6. It's 6 on foobar. Okay. So, Baz, cuz, yep. So basically when the linker runs, it reads the symbol table, compiles them all together, and goes through all the undefined references, being like, all right, can you find everything? If you can find everything, it builds an executable for you. There you go. If you can't find something, then it will output undefined reference, and it will say this thing here has an undefined reference. And then it doesn't compile an executable for you. Okay. So does this work for you guys? You understand linkers a little better now? All right. Yeah, and if you're ever curious about that kind of stuff, there's different executables that will different Unix utilities that will tell you information about the symbol tables. Linker errors are some of the most annoying things to deal with in C++. Let me just give you a simple example. Vim a.h and x. Okay, here's a header file. What's in the header file? An integer. Okay, you guys with me? That's the whole header file. A.h. Got it? All right, so let's say we've got a thing called a.cc, and it's got main, and it's going to see out the value of a, include a.h. Okay, so you guys remember how includes work? It's just going to copy and paste that file. Bloop. Okay. So what value is this going to print out? So a.h is, this is literally the same as if I just typed int, like it's literally the same as if I typed int a. Like that. You know, I could literally comment that out, just have int a there. It's the exact same thing for all intents and purposes. So what value is this going to print? What value does a have? It is never an errand to have an uninitialized variable in C++. It is an error in Java. If you try printing the value of an uninitialized variable in Java, you will in fact get a compile error. In C++, it is not an error. However, this is not uninitialized. In C++, globals are 0 initialized. Okay? So it's going to print 0. It's not printing a memory address. It's just going to print 0. So, using. What just happened? A is not declared in the scope. What did I do? Oh, I made it X. Okay. Fair enough. There we go, print 0. Okay. Didn't know that about globals. Welcome to 4th semester computer science. We give you the details. Give you the deets. Okay. Okay. No surprises here except for, I guess, the globals being 0 initialized. Let's make another function, and we're going to call this one b.cc. And b.cc is just going to be a function named Bob, and it's just going to return the value of a. Who's this a fellow? This one right here. So do you guys all agree this is just returning 0? Function returns 0. All right. As I'm in IO streams, there's no using namespace, just literally return 0. Yesn't? You don't think so? You think this is a trap? 50% chance of being right. You guys are gun shy now? It's returning 0, right? Like it's not. Yeah, that's not the problem. It is going to return 0. So like if we main cout Bob, prints out 0. I don't know why you guys are so suspicious. Now, what would happen if I tried this? G++, a.cc, b.cc. Is it going to be happy with there being 2 different mains? Is that cool? Because remember, there's a main in a.cc and there's a main in b.cc. Is that gonna work? Is that gonna fly? Is it compiler error or linker error? Is the compiler going to be mad at us or the linker going to be mad at us? In C++, are you allowed to have 2 functions with the same name and the same parameters? You are correct. It is a compiler error. So if we do this, then it's actually a, well, if they were in the same file, it would be a compiler error. It is a linker error because we've got 2 different multiple definitions of main. Because remember, each one of these files compiles separately. So if we had 2 mains in the same file, it'd be a compiler error. But each one of these gets compiled separately, so it gets turned into a .o file. So this fellow here is the temp.o file that's made. And then there's also this temporary.o file, which is a.cc. And this is presumably b.cc. It's temporary file. And so it's like, hey, this one has a main, this one has a main. I'm trying to put them together, and there's a main in this one, there's a main in this one. It doesn't work. Sorry, you've got a redefinition. Okay. And it's angry about other things as well. So, okay. So both be a compiler and linker. Now in this case, it's only a linker. The C++ standard is not allowed having 2 functions with the same name and the same parameter list in the same file. If they're in different files, it's a linker error because C++ compiles 1 file at a time. It technically is called a translation unit because it's not just a file when you include things. So when you include things, you're actually bringing things in from other files as well. So it's called a translation unit, which is it's a file, a.cc. Right? So in this case, yeah, so it's a compiler error if they're in the same file. It's a linker error if they're in 2 different files. All right, so let's fix this b.cc, and let's just do this. Okay. So now let's go into a.cc and have it cout Bob. And we're going to compile it like that. Is this going to compile? Will this compile? Yes, 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 yes. Nope, it won't compile. It has never heard of this Bob fellow before. We try compiling a.cc. Error, Bob, who, what? Remember, you have to know the prototype of a function in order to call it. In C++, you must declare a function exists like that. Okay. So you have to tell it, hey, there's a function out there somewhere named Bob. You do that, it will now compile, but it won't link, right? Because you're telling it there's a function out there named Bob, and you didn't give it Bob. So when it comes time to actually make an executable, it's like, hey, did anyone ever see this Bob fellow? Never saw him. So the linker is like, yeah, you told me, dude, there's going to be this Bob out there somewhere. Couldn't find it. If we, however, compile it like this, then we have, then that part's fine. But now we've got what I kind of wanted to show you, multiple definition of A. A multiple definition of A. It's defined in just one place. It's defined here. Hey. Right? How's it a multiple definition? Well, let's take a look at the name table. Simple table. See that? So a.cc has heard of this A fellow, right? Because this, right? Do you guys know what segment globals are held in? Are globals held in the stack or on the heap? 50-50. Roll those dice now. May the odds always be in your favor. This is a global, right? It's an int. A, right? It's a global. Is this held on the stack or on the heap? Got 3 people voting for heap, 1 person voting for stack. Gregorian is too afraid to say anything. 3-to-1 odds on heap. Pata, Prado, Serhang, heap, Corrente, stack. Prado's pleading the 5th. Stack. So we got 3-4 votes for stack. Mincarelli says globals are usually stored in the stack. Corrente likes stacks. So I think stack's beating out heap. Any other votes coming in? Matt Coppedge. No clue from Blake. Stack. Okay. So 50-50. Who was right? None of you. It's stored in a different segment called the BSS. So the BSS is the the BSS is the segment the globals are stored in, and there's so I don't even know what the BSS stands for. BSS segment. Global and static variables are stored in the data segment, and initialized data in the BSS segment. What do we have a dedicated segment for uninitialized variables? What does it stand for? Better save space? No, that's wrong. That's not what it stands for. There we go. Block starting symbol. Okay, that's completely non-meaningful. Block starting symbol. It's a term from the 1950s Yeah, so if you guys remember this picture of memory that I've used many times with you, stacks on top, heaps down below, your code segment, the text segment is down here. And then below the heap, there is the BSS. And you have, it's cut into two parts. There's uninitialized and initialized. There's also like read-only data, which is called row data, RO data, like reverse osmosis data. So there's a couple different areas where like globals and things like that are held, but yeah, so this is going to be in the BSS. It's uninitialized. It's an uninitialized global integer. And so when we, why is everyone so suspicious of me? Yeah, so just do that right here. So if you look up here, you can see that A is held in the BSS. Okay. Now if we nm b.o, you can see that b.o also has a variable named A in the BSS. So you got a problem here. You got a problem. The problem is that both of them have a variable named A, and you cannot have two different .o files with a variable with the same name. That is a bad. Yep. If we g++ a.o b.o, then we get a multiple definition error. So that's a problem. Okay. So we have two people, including the same file, right? And because we're both including the same file, we both got a copy of A, and those get baked into our .o files. So when we try linking the .o files together, you get a multiple definition error. Okay. So this is what I mean by like linker errors are the devil's own error. Okay. Can't you get that if you call the same header file in two other header files? Yes. But no. It kind of depends. Like, what happens if you include this twice? Right here, let's just simplify this down. What if we include the same header file twice? What's going to happen? Yep. It's like we wrote this line, A and A twice, right? So, yeah. But that's a compiler error, because the compilers noticed that you included the same thing multiple times. So there is this thing called pragma once, and this means if I get included multiple times in the same translation unit, don't. Only allow me to be included once in a translation unit. And so that'll solve one of the problems, but it won't solve this, because each translation unit has, it can only be included once in each translation unit, but we got two translation units, and so they each have their own notion of who A should be, and it's not good. If you want to see why it matters, what if we did this? You guys see what the problem is? So main thinks that A is supposed to be an integer, and B thinks that A is supposed to be a float. You can only have one name, right? So if you try doing this, which one's right? I don't know. You understand? So that's why you can't just, be like, all right, it's just the same thing, I guess. I don't know. Like, both of them have a global named A in the BSS, and one's an int, one's a float. Which one's right? I don't know. So it's a problem. It's also a problem if you do this. Okay. So a.h now doesn't have a global variable, it has a function. And so you'd think like, okay, this will solve it, right? Because a function, it's okay to have the same function included multiple times, right? Everybody includes cout. It's not a big deal. Nope. Can't have the same function defined. Right? This function here is included in A, it's included in B. Like you're redefining a function. Can't do that. The linker doesn't know which one's supposed to be the right one. And if you want to think about why that's a problem, imagine if you compile A with the header like this, and you compile B with the header like this. Both of them have Bob baked into it, and they're different. So which one's the right one? Don't know. And so the linker doesn't allow it. So there's a problem, you know, because you want to put functions in headers, right? Like my header library, right? It's got functions in it, right? So the solution is to make it inline. So if you make it inline, and it works fine. So if we look at it now, we're calling bar, and we know about this Bob fellow somewhere, I think. Might have been inlined out, actually. Okay, there we go. So there's Bob. Why is Bob not in here? Oh. So you see how Bob, this inline function, you see how it's now a weak reference? So weak references are allowed to be redefined. Okay. If you have a regular reference, like you make a function and you include it twice in two different files, you try linking them together, it will not allow it because you can only define a regular reference once. You can only have a variable once. You only have a function once, defined once. You can, yeah. But if you make it inline, it becomes something called a weak reference, and weak references can be duplicated. And it's on you to make sure that they're the same in every different version. A weak reference means, yeah, every time Bob shows up in a .o file, it's the same Bob, trust me. And if it's not, oh Lord, help you. Because it'll just pick one of them to be the right one. So if in one of them you compile it with Bob returning 42 and another one returning 40, it'll just pick one of them because it's a weak reference. There's no one right one. And so for those of you that have heard of inline before, a lot of you have probably thought of it as an optimization thing, right? Have you guys heard of this before? The inline keyword? Have you guys, anyone heard of this before? So we normally think of it as like an optimization thing, which means remove the function overhead. Now that you guys are starting to learn assembly, do you see how there's like an overhead to doing a function call? You have to do a branch with link, 8 cycles, let's say, in cost. You jump to Bob. You then push all these registers onto the stack. You then move 42 into register 0. You then pop the registers off the stack. and then you return to the link register. That's a pretty big overhead, right? Maybe you don't save all the registers, maybe you just save the link register and restore it into the program counter, but you're still talking about a cost of like 13 cycles when it should be 1, right? If you call Bob from main, it should just remove the function call entirely and just put 42 into X or whatever, right? So you can see that it is going to probably call Bob here. So with the unoptimized code, it's calling Bob. If we optimize it, it should be inlined away. When you inline away something, search for Bob, there is no calls to Bob anywhere within this code. The reason for that is because it has been inlined away. When you inline a function, that means you remove the function call overhead and you just copy the body of the function into main here. You guys see that? You guys see what happened here when I turned the optimizer on? I was doing a function call, and function calls normally have quite a lot of overhead, you know, especially for a one-liner. That's a lot of overhead for a one-line. And so what the optimizer will do is if you have a very small program, it'll actually take the body of the program from the function and then put it into main, or whoever it is that's calling the function. Do you see that? It's way faster. It's like 10 times faster, so order of magnitude faster. It's especially important if you're doing the function call a lot of times, right? Does this make sense? And that's what people think of inline as doing. Okay? That was sort of the historic use of the inline keyword. The historic use of it is to tell the compiler to inline it. To don't do a function call on me, just pull the code on the inside out and put it in main, and don't call this function at all. Just anytime there's a call to Bob, replace that with return 42, or the number 42 technically. Okay. Nowadays it doesn't mean that. The optimizer is smarter than you usually, and so if you see the inline keyword now, what that means is make it a weak reference. Allow it to be included in multiple files. Make Curly, does this make sense to you? If you do inline, you can include it in multiple files. So that was a problem I had with my read library, actually, was that include public read.h. I haven't actually tested this recently, so let's see if it still works. Aha. Read line. Not marked as inline. See that? Multiple function read. Yeah, why is this? I thought I fixed this already. I'll have to check the GitHub. I thought I fixed this already. All these should have been inline a long time ago. Yeah, weird. So now my header file works if it's included multiple times. I think it's fixed on GitHub already. I might not just have updated it on the server. Do you see that? So because I included my readlib for multiple files, I was getting linker errors for redefinitions. But by marking all of the functions as inline, it works now. So what's the lesson of the story? If you're doing a header file and you're having your actual functions in the header, mark them as inline, and then they can be included in multiple translation units. Okay, some practical programming tips right there. You thought you were just here to learn assembly, but you got to learn about linking. You got to learn about the deep dark secrets of C++. You learned about the BSS, the whatever the hell that stands for, and you learned about function calls today. So I would like for you guys to write a function now. We'll do a little lab time. I'd like for you to write a function that will do Fibonacci. Okay. So let me put up lab time. So I've been talking for a long time. I'm done talking. This was a big topic today. How to do functions is basically you're good. The only thing left to learn in assembly is like how to do arrays and classes, and we can put that off to another time. But how to do a function call, that's huge. How to link things together, like especially linking together assembly in C or assembly in C++ with the externc thing. So write two files, make two files. One in assembly with main, and one in C or C++. If you use C++, you have to use externc. The assembly code should print the C++ code. Now, people hate it, by the way, when you do this. If you ever put that on a resume, that will trigger some people, because they're like, C and C++ are two different languages, and it's like, yeah, they are kind of, except C++ can kind of do C, but like people will say, well, if you do that, then you're just saying you don't know the difference. And yeah, I actually mean here either C or C++. So the C or C++ code should do your I/O. So your CINs or scanfs and your couts or printfs. Okay. Everything else in assembly. And I want you to read two integers, start and end indices, and your code should print out the Fibonacci. So for example, if you type in 0, we'll just 0 index it, and 5, it will print out, example input, will print out 1, 1, 2, 3, 5. Okay. Five to 10. We'll print out, let's see, 0. 8. Sorry. 0, 1, 2, 3, 4, 5. There. Okay. So it'll print out 8, 13, 21, 34, 55. 89, let's see, what index am I on? 6, 7, 8, 9, 10. Okay. I think that's right. Should the assembly code be the .h file? No, it should be a .s file. So your assembly code is usually held in .s files. Okay. You don't need header files in assembly. Header files are usually used in C and C++ to tell you which functions exist. Usually a header file A header file usually looks like this. Int foo semicolon. That way you don't have the problem with multiple redefinition errors, right? You just say this function exists, that's fine. You can say int foo 5 times. That is a-okay in C and C++. You just say, hey, this function exists, cool. But if you define it, this is no longer allowed. Okay. They started the Fibonacci sequence as 0. Whatever. We'll just go with this. Okay. All right, you guys got till 12:30. Have fun. If you have any questions, just ask me. And before you leave, screenshot your code and post it on the chat channel. And once you finish it, you can take off. Sir, that's the README. Yeah, Betancourt, why did you post a screenshot of the README? So you can see it at work. That's fair. Okay, so I'm just going to go ahead and pause the stream now. Okay, and we'll come back at 12:30 and see what you guys did. All right. So, who got it done? Printf used arrays, which are not necessary. You only need 2 variables really to do Fibonacci. So Betancourt had an issue where he was printfing, but he was printfing using the address of the variable instead of the variable itself. Scanf takes an address. So, yeah, SOSA, I would start with, you know, the code in the demo code in 7 and just work from there. Let's call readin. Let's see. Yeah, so scanf takes the address of something like this. Printf does not. Okay, so Printf just takes regular variables. So I do appreciate the fact that you're trying to use you know, scanf and printf because you're learning something. Whereas I think a lot of people are just sticking with C in and C out because they're comfortable with it. So, like I said, the format string method of printing things is actually pretty common in computer science, and it's probably a good thing to learn. Like, it just crops up in a lot of places. So, branch if less than or equal. Okay, so let's take a look at Shahab's code. Shahab is pushing these things and doesn't have a pop at the end. So remember, every push needs a pop. They're symmetrical. They need to be symmetrical. Putting 0 into 4, 1 into 5, 0 into 6. Branch of no. That's not the format for branch of less than or equal to. Go back and look at the lecture for last time. You do a comparison between 2 registers, and then that sets the CPSR, the comparison status register. And based on the results of that comparison, you can do a branch of greater than, branch of less than, and it takes a label as a parameter, not registers. Yeah. Let's look at SOSA's push, pop. That looks symmetrical to me. Cool. Main, moving these variables in here. Branch with link into input, moving the variable thing out. Branch with link into everything out. Comparing 9 and 5. If 9, okay, 0. So comparing 0 and 5, if it is less than or equal to, it jumps to top. Okay. Do you mean to compare like 4 and 5 maybe? Because that's the first index, that's the second index. If it's not, then you quit. Is it still segfaulting, Annalisa? Godbolt did help. It's trying to miss in person. Got the algorithm working. Don't know how the ranges. I thought you had to use sus. Oh wait, no, subs. You do not have to use sub. The S suffix is just a shortcut that eliminates the need for a comparison with 0. Anytime you see yourself doing a comparison with 0, oftentimes you can use a S to kind of cut out a line of code. So is it crashing? Is it crashing, or is it just not working correctly? Output. Oh, that's your problem. Yeah, a function call is branch with link, BL. So if you want to do a function call, it's BL. If you want to jump to a label, it's B. And that is something that everyone makes that mistake at some point or another. If you branch without a link, then it's not setting the link register. That's what BL does. BL sets the link register so that when you do a pop from the link register into the PC, it comes back into the next line of code. So when you do a BL, it saves this spot in memory, so that when you return from a function, it comes and runs the next line of code here. So that's a branch. If greater than, it goes there without setting the link register, and so it's going to segfault or something. I don't know. Who knows what will happen? It's undefined behavior. Top is fine. Exits here. So compare R9. So you're adding 1 to it each time, and if it ever is greater than 5, then it quits. Okay, yeah. In general, it looks fine to me. Right, add 6, subtracting, comparing. Yeah, you can just kind of move from one to another if you want. Compare, add. So that's your loop counter. Okay. So that's I, that's J, and then that's your loop counter that runs from I to J. I think that should be R4 then, because you're going to be wanting to compare, or maybe you want to start R9 at R4, because right, you start at 5 and go to 10. And right now R9 is kind of the iteration number, which is not this, like if you're running from like 1 million to 2 million, I starts at 0 currently. So yeah, so I would probably initialize R9 to be R4 after you do this. I don't know. Okay. C++ version. Yeah, you can do it that way, but you can just move the variables. I don't know. It's up to you. It's probably a little bit faster the way you're doing it. So the format is compare before doing the while loop statement. The format is anytime you do a loop, you're going to do a comparison and then a branch. And so here we're doing a subtract, so we're counting downwards from 5 to 0. And if we ever hit 0 or less than 0, then we branch to done. This one line of code here is the same as those 2 lines of code there. They're equivalent. There's no benefit to doing it this way, actually. It's just slower. It's twice as slow as this. But if you don't understand the subtract suffix, then just use comparison. Yeah, so the general pattern is you do a comparison, then you do a branch. That's kind of your go-to way of doing an if statement. And then when you have a loop, the branch always just takes you back up to the top of the loop. So we got a way out here. This is where we're checking to see if we're done. This is the body of the loop, and then at the bottom of the loop, we just go back up to the top and do the top again. So like when you say while x is less than y, you do the comparison, If you're done, you bail out of the loop. Otherwise, you run the loop and you go up to the top and do it again. Use subs for input checking. Subs for input checking? I don't see how. For input checking, remember, it's not subs. It's not subs. Like, it's just the s suffix. You can put an s suffix on anything. You can do a move and set. You can do moves. There's nothing to do with subtraction in particular that goes with the s. S goes with anything. You can do a you do a move and set if you want. That's perfectly fine. And then it'll compare R4 with 0, and if you did this and you did a branch if greater than to done, this code would come here, compare R4 with 0 after it sets it to 1. Yep, it's greater than 0, and so it'll jump down here and quit out of the program. So this would bypass the entire code, basically. Okay. Yeah. BLT is less than 0 if you're using the s suffix. The s suffix compares it with 0, but it just means less than. So when you do a comparison, it compares the first thing and the second thing, and then it'll do the branch if less than, if the first thing is less than the second thing. So it doesn't have to do with 0 necessarily. With the s suffix, it's comparison with 0, but you could always compare like R5 and R6, and then branch with less than would take place if R5 is less than R6. Okay. All right, so yeah, we're out of time. I'm going to give you guys another homework assignment, real easy. I think just getting a little more practice with loops would be good for you based on the assignment. So you're going to write FizzBuzz in assembly. So FizzBuzz is a program in which you print out the numbers from 1 to 100. It's a classic job interview problem. If the number is divisible by 3, you print out fizz instead of the number. If the number is divisible by 5, you print out buzz instead of the number. And if it's divisible by 15, you print out FizzBuzz instead of the number. How do you do modulus in ARM? That's a great question. Main.c. Figure it out. No, you've not learned it. Deploy homework, CSI 45, asm FizzBuzz. So, figure out how to do modulus. There is no modulus command in ARM32. That's the hardest thing in the assignment. But I would start off by making the loop run correctly, print out the numbers from 1 to 100, and then see if you can figure out how to do divisibility. Okay. I'll give you a hint. I don't use modulus at all. You cannot do mod with C and C++. Nope. All you can do with C and C++ in this class, unless I say otherwise, is I/O. So the like as you saw in my thing right there, vim main.c, the printing of fizz and buzz and the numbers, do that in C, C++. That's it. This is all that's allowed. You can't modify this file either, and this is all you can use in C. So it's got a function to print fizz, buzz, and a number. It's got a debug function if you want to pass in R0, R1, R2, R3. It'll print 4 numbers at once for you, just in case you want to see what the numbers have. Yeah, but everything else needs to be in FizzBuzz. So FizzBuzz needs to be a while loop that will print the numbers from 1 to 100, following the rules for FizzBuzz. And I will tell you, you don't need modulus to do this. You could write your own modulus thing, but you don't need it. It's possible to do this without any use of division or modulus whatsoever. I'll let you try and figure out how to do that. It's going to be slower in ASM because loops. No, I mean it should have the same running time as C++, if not faster. Run incredibly quickly. -03. Look at how fast that run. Look at how fast that run. 0.008 seconds. That is light. That is the fastest FizzBuzz implementation ever. All right. So that's the only hint I'm going to give you as far as modules goes. You don't need modules. Okay. So that'll be due next Thursday. It's an easy assignment. Just do a loop or something. You ever gonna remember class starts at what time does the class start? Oh yeah, at 1. Okay, all right. See you, 45 people. It is now CSI. I is 50 people time. All right, peace out.